In vector calculus, divergence is a vector operator that measures the magnitude of a vector field source or sink at a given point, in terms of a signed scalar. More technically, the divergence represents the volume density of the outward flux of a vector field from an infinitesimal volume around a given point. For example, consider air as it is heated or cooled. The relevant vector field for this example is the velocity of the moving air at a point. If air is heated in a region, it will expand in all directions such that the velocity field points outward from that region. Therefore, the divergence of the velocity field in that region would have a positive value, as the region is a source. If the air cools and contracts, the divergence has a negative value, as the region is a sink. Definition of divergence. In physical terms, the divergence of a three-dimensional vector field is the extent to which the vector field flow behaves like a source or a sink at a given point. It is a local measure of its outgoingness, the extent to which there is more exiting an infinitesimal region of space than entering it. If the divergence is non-zero at some point, then there must be a source or sink at that position. When we use the terms flow, sink and so on, more rigorously, the divergence of a vector field f at a point P is defined as the limit of the net flow of f across the smooth boundary of a three-dimensional region, V divided by the volume of E as V shrinks to P. Formally, where V is the volume of V, S is the boundary of V, and the integral is a surface integral with n being the outward unit normal to that surface. The result, divf, is a function of P. From this definition, it also becomes explicitly visible that divf can be seen as the source density of the flux of f. In light of the physical interpretation, a vector field with constant zero divergence is called incompressible or solenoidal. In this case, no net flow can occur across any closed surface. The intuition that the sum of all sources minus the sum of all sinks should give the net flow outwards of a region is made precise by the divergence theorem. Application in Cartesian coordinates. Let x, y, z be a system of Cartesian coordinates in three-dimensional Euclidean space, and let I, j, k be the corresponding basis of unit vectors. The divergence of a continuously differentiable vector field f equals ui plus vj plus wk is equal to the scalar-valued function. Although expressed in terms of coordinates, the result is invariant under orthogonal transformations, as the physical interpretation suggests. The common notation for the divergence f is a convenient mnemonic, where the dot denotes an operation reminiscent of the dot product. Take the components of the operator, apply them to the components of f, and sum the results. Because applying an operator is different from multiplying the components, this is considered an abuse of notation. The divergence of a continuously differentiable second-order tensor field is a first-order tensor field. Cylindrical coordinates for a vector expressed in cylindrical coordinates is where each is the unit vector in direction A. The divergence is spherical coordinates in spherical coordinates, with the angle with the z-axis and the rotation around the z-axis. The divergence reads Decomposition Theorem. It can be shown that any stationary flux V which is at least 2 times continuously differentiable in and vanishes sufficiently fast for R infinity can be decomposed into an irrotational part E and a source-free part B. Moreover, these parts are explicitly determined by the respective source densities and circulation densities. For the irrotational part 1 has with the source-free part B, can be similarly written. One only has to replace the scalar potential phi by a vector potential A and the terms minus phi by plus times A, and the source density divV by the circulation density times V. This decomposition theorem is in fact a byproduct of the stationary case of electrodynamics. It is a special case of the more general Helmholtz decomposition which works in dimensions greater than 3 as well. Properties. The following properties can all be derived from the ordinary differentiation rules of calculus. Most importantly, the divergence is a linear operator, i.e., for all vector fields f and g and all real numbers a and b. There is a product rule of the following type. If is a scalar-valued function and f is a vector field, then or in more suggestive notation another product rule for the cross product of two vector fields f and g in 3 dimensions involves the curl and reads as follows. Or the Laplacian of a scalar field is the divergence of the field's gradient. The divergence of the curl of any vector field is equal to 0. If a vector field f with 0 divergence is defined on a ball in R3, then there exists some vector field g on the ball with f equals curl. For regions in R3 more complicated than this, the latter statement might be false. The degree of failure of the truth of the statement, measured by the homology of the chain complex, serves as a nice quantification of the complicatedness of the underlying region U. These are the beginnings and main motivations of the RHAM cohomology relation with the exterior derivative. One can express the divergence as a particular case of the exterior derivative, which takes a 2 form to a 3 form in R3. Define the current 2 form. It measures the amount of stuff flowing through a surface per unit time in a stuff fluid of density moving with local velocity f. Its exterior derivative is then given by thus, the divergence of the vector field f can be expressed as. Here the superscript is one of the 2 musical isomorphisms, and as the Hodge dual. Note however that working with the current 2 form itself and the exterior derivative is usually easier than working with the vector field and divergence, because unlike the divergence, the exterior derivative commutes with a change of coordinate system. Generalizations. The divergence of a vector field can be defined in any number of dimensions. If in a Euclidean coordinate system where and define the appropriate expression is more complicated in curvilinear coordinates. In the case of one dimension, a vector field is simply a regular function, and the divergence is simply the derivative. For any n, the divergence is a linear operator, and it satisfies the product rule for any scalar-valued function. The divergence can be defined on any manifold of dimension n with a volume form, e.g., a Riemannian or Lorentzian manifold. Generalizing the construction of a 2 form for a vector field on such a manifold, a vector field X defines a n-1 form obtained by contracting X with. The divergence is then the function defined by standard formulas for the Lie derivative. Allow us to reformulate this as this means that the divergence measures the rate of expansion of a volume element as we let it flow with the vector field. On a Riemannian or Lorentzian manifold, the divergence with respect to the metric volume form can be computed in terms of the Levi-Civita connection, where the second expression is the contraction of the vector field valued 1 form with itself, and the last expression is the traditional coordinate expression used by physicists. An equivalent expression without using connection is where is the metric and denotes partial derivative with respect to coordinate. Divergence can also be generalized to tenses. In Einstein notation, the divergence of a contravariant vector is given by where is the covariant derivative. Equivalently, some authors define the divergence of any mixed tensor by using the musical notation hash. If T is a tensor, then we define the divergence of T to be the tensor, that is, we trace the covariant derivative on the first 2 covariant indices.